Now we're going to look at a microscopic theory for an ideal gas. It's called kinetic theory, and this theory comes with a set of assumptions that we have to familiarize ourselves with. So let's take a look at the assumptions of the kinetic theory. So we can summarize our assumptions in five items. The first item is that the number of molecules in the gas is very large. So we have n, the number of molecules in the gas. It's very large. It's of the order of Avogadro's numbers, 6.02 10 to 23. So it's a very large number. And the average separation between the molecules is very large compared to the molecule size. So basically this is saying you have lots and lots of molecules, and the molecules are point-like particles, and they have quite a large distance between them. The second item is that they obey Newton's laws of motion, but as a whole they move randomly. So we have random motion, and they obey Newton's laws of motion. When they do interact, they obey Newton's laws of motion. So we're treating them classically. Now, how often do they interact? They interact very rarely because there's a large separation between them. But when they do interact, it's by short-range forces that are developing during elastic collisions. So we have elastic collisions between molecules and short-range forces. So this only happens very rarely. When they come really close together, we have the short-range forces coming into play, and the change in energy of the molecules, kinetic energy of the molecules, is zero. And number 4, they also make elastic collisions with the walls of the container. So elastic collisions between molecules and the container walls. And number 5, we have all molecules identical and the gas is pure. So pure gas, identical molecules. And you can see that this, basically the picture that we're drawing here says that these molecules are like points. They are moving randomly inside a container. So we have a random direction for the velocity of each point. Like this. And when they do collide between themselves or between the walls of the container, those are elastic collisions, and they also obey Newton's laws of motion. Now, if you're thinking about a real gas and how well this model fits to this real gas, I need to remind you that all gases are like ideal gases. When we have low density and low pressure conditions satisfied, we have all gases behaving almost like ideal gases. Alright, so let's start trying to calculate the pressure of the gas exerted on the walls of a container. So let's say that I have n molecules of an ideal gas, n molecules, ideal gas, container, it's in a cubic container, volume V, that's equal to d cube, because the side of this cube is d. And let's concentrate on one molecule that is approaching the right side wall with a velocity v initial, so that it has an x component vxi. And why do we have I? Basically, we're looking at the ith molecule. So this one is the ith molecule. So we're concentrating on the ith molecule in this gas. Now, when this molecule comes and hits the right wall, its momentum is going to change. And how does it change? Delta P xi will be pxi final minus pxi initial. So this will be minus m0 vxi minus m0 vxi, so total minus 2m0 vxi. Why is that? Because pxi final will be equal to minus m0 vxi final in minus I hat direction, and pxi initial is m0 vxi initial in the I hat direction. So the initial and final speeds, vxi initial will be equal to vxi final, because we have elastic collision, kinetic energy conservation. So we will have the momentum change minus 2m0 vxi. Alright. And the change in momentum is due to the force that is applied by the wall during the collision, and we have basically linear momentum, impulse momentum theorem. So I'm going to use the impulse momentum theorem, which states that the impulse that is applied by the wall is the force, the wall average force it applies during the collision, times delta t of the collision, the time of the collision. And this must be equal to the change in linear momentum of the ith molecule. So let's basically clarify. This is the force, the average force exerted by the wall on the molecule. And we have delta t collision time. So this force appears only during the collision time. And this is going to give me the change in x component of linear momentum minus 2 m0 vxi. So what is m0? m0 is mass of one molecule. Remember, they are all identical molecules, so they all have the same mass m0. Okay, so let's say that this collision has occurred. Then I ask myself, how long does it take for a similar collision to occur with this wall, between this wall and this molecule again? So basically, once this molecule reflects from this wall, it has to go all the way back to the other side, and then it's going to reflect from the other side, and then it has to move all the way back to this wall again to hit the wall. So what is the distance traveled by this molecule in between the collisions? Well, it's going to travel a distance d on the x-axis to hit the other side, and then it's going to travel another distance d to come back and hit this wall. Alright, so let me redo this drawing just to make sure that I'm not confusing you. This is basically on the x-axis, so this molecule is moving to hit this wall, and then it's coming back. I'm looking at the x component of its velocity to hit the same wall again. So the distance traveled is 2d. Alright, so I call delta t a time interval between two successive collisions. So I'm talking about collisions with the same wall and same molecule. Therefore, this delta t is going to be 2d, the distance traveled, divided by vxi, the x component of the velocity of the ith molecule, because the molecule has to travels in minus d I hat and plus d I hat to hit again the same wall. All right. So if I average the force exerted by the wall on the molecule, on the ith molecule, so I define a new force, Fi bar. It is the force exerted by the wall on the ith molecule, averaged in time interval delta t. So instead of using this collision time, which is hard to know exactly, it's such a small time, we're going to average the force over the time interval between two successive collisions. So I'm going to rewrite the impulse. The impulse was, remember, F bar collision times delta t collision. Now I'm redefining the force to be Fi bar and the time interval delta t. So this will be equal to minus 2m0 vxi, and therefore I find that this force Fi bar is minus 2m0 vxi divided by the time interval delta t, which I have found to be 2d divided by vxi, so I can substitute that here, and I will find this is minus 2m0 vxi divided by 2d over vxi, so I will get minus m0 vxi squared over d for the ith molecule, the force exerted by the wall on the ith molecule. Then I ask myself, what is the force exerted by the ith molecule, average force exerted by the ith molecule on the wall? I can use Newton's third law, action reaction, tells me that the average force I'm exerting on the wall, the force exerted by the ith molecule on the wall, average force exerted by the ith molecule on the wall, this will be equal to minus Fi bar, the average force exerted by the wall on the ith molecule. So this force will be equal to m0 Vxi squared over d for the ith molecule. And it's the same force for each molecule because the molecules are identical. So this will be the same on average. Now, what is the total force exerted on the wall by all of these molecules? So total force exerted on the wall will be the sum of all the forces exerted by n molecules, and each of them has a x component of its velocity Vxi. So I'm summing over all the molecules in order to calculate the total. So this will be the total force. All right. So I have a very large number of molecules, of the order of Avogadro's number. So the molecule to molecule variations are smeared out, and it is random. So I can calculate what is the average value of Vx squared. It is the sum from 1 to n Vxi squared. For all molecules, I take their x components of the velocities, square them, add them up, and divide it by n. So this gives me the average of Vx squared. So I can write, instead of single molecule velocity Vxi here, this will be equal to the force total the total force exerted on the wall is m0 over d multiplied by n Vx square bar. So I have substituted for sum over I equals 1 to n Vxi squared, n times, capital N times Vx square bar. And now I ask myself, what is the relationship between x component of the velocity and the velocity squared? So I have, for the ith molecule, the ith molecule speed is Vxi squared Vyi squared plus Vzi squared, with all components equally probable. Why am I saying this? Because the motion is random motion. So I had this assumption in my kinetic theory. So you see, the motion is random. All right, so if I take the average of v square, so this is going to be equal to average of Vx square, average of Vy square, plus average of Vz square, and where I will have Vx square average is the same as Vy square average is the same as Vz square average, so that the V square average is 3 times Vx square average, because I have random motion. So if I go back to this equation, I write the total force exerted by the gas molecules on the wall will be m0 over d times n v square bar divided by 3 for Vx square bar. That's the average. And also pressure is force divided by area, perpendicular area. So it's the force per area of the side here. So that is this area A. So I can calculate the pressure to be F divided by D squared is equal to M0 divided by D cube and V square bar divided by 3. Now I want to rearrange this equation. First of all, I note that I have D cube here. The volume of the container is D cube. So it is M0 N over V. I have a factor 1 over 3 here, V square bar. Then if I stare at the rest of the terms here, I have basically something that looks like the average kinetic energy per molecule. So I can say that this is 2/3 N over V 1 over 2 M0 V square bar. And N over V is called number density, N sub V. So it's the number of molecules per unit volume. So I can write this as the pressure exerted by the gas molecules on the walls of the container is 2/3 number density times the average kinetic energy per molecule. So this allows me to calculate the pressure of a gas. So the pressure of the ideal gas is proportional to the number density, the number per unit volume, and the average translational kinetic energy. So this is average translational kinetic energy, because it's 1/2 mv squared per molecule. And this is number density, total number divided by the volume. So that's what determines the pressure. So does that make sense? If you think about it, if the molecules have a higher kinetic energy, they're more likely to hit the sides of the walls, and so they, on average, they will have a larger pressure exerted on the walls. And if you increase the number of gas molecules in the same container, then you have more frequent collisions, and also you expect that a higher pressure would be applied to the walls of the container. Now, if we take this calculation one step further, now that I know the pressure is given by this equation, 2/3 number per volume, 1/2 m0 v square bar, I want to write ideal gas law. So what is ideal gas law? Pressure times volume is number of molecules times Boltzmann constant times temperature. So if I take this equation, multiply it with volume, I get PV is equal to 2/3 N 1 over 2 m0 v square bar. And according to the ideal gas law, this should be equal to N kBT. So this is going to tell me that the temperature is equal to 2/3 Boltzmann constant times the average translational kinetic energy per molecule. So that this is just a constant, and therefore it says on the molecular level, temperature is something that is proportional to the average translational kinetic energy per molecule. So finally, I have a molecular scale interpretation of temperature. I know that the temperature is basically a measure of average kinetic energy per molecule. Now, on the other hand, if I look at this equation more closely, I realize that 1/2 m0 v square bar is 3 over 2 kBt. All right. And since I have v square bar is equal to 3 times vx square bar, this also implies 1/2 m0 3vx square bar is 3 over 2 kBt. So the 3's cancel. I find 1/2 m0 vx square bar is 1 over 2 kBt. And the same is true for vy square bar and vz square bar. And this is a very profound result. It's known as the theorem of equipartition of energy. Basically, this is the theorem. Each degree of freedom contributes 1 over 2 kBt to the energy of a system. Of course, we're talking about the internal energy, where possible degrees of freedom are associated with translations, rotations, and vibrations. So this very important result, known as theorem of equipartition of energy. So theorem of equipartition of energy. We have just shown this theorem for basically the translational degrees of freedom, but it's more general than that. Okay, so what is the total translational kinetic energy of this gas? I have average per molecule is 1/2 m0 v square bar. So if I multiply this by n m0 v square bar, I get 3 over 2 n kBt. This, or 3 over 2 number of moles universal gas constant times T. Remember, R is equal to Avogadro's number times Boltzmann constant. And if this is a monatomic gas, that means we have only translational degrees of freedom, and the internal energy, remember, is just a measure of the translational, rotational, and vibrational kinetic energies of the atoms when viewed from the center of mass reference frame. So this is just telling you that it only depends on two things: the number of molecules and the temperature. This is an important result. The only way you can change the internal energy of a system is by changing the temperature or changing the number of molecules in the system. The total internal energy will change. Now, one more important result that comes out of this is basically V square bar. V square bar is called the root mean square speed. Root mean square, or RMS speed. And what is it equal to? Using the equipartition theorem, from this equation, basically I get that V square bar is equal to square root 3 kBt divided by m0. So I can rewrite it here: V square bar square root of V square bar, is the root mean square, is square root 3 kBt divided by mass of one molecule, or if you want to write it in terms of the universal gas constant, it's 3 RT divided by capital M, the mass of one mole. That's the molecular mass. So capital M is molecular mass. So this is telling me the root mean square speed is determined by the molecular mass. So if a molecule is light, then it's going to have on average a higher speed. So lighter molecules, that's an important conclusion, light molecules move faster on average. For example, if you look at the composition of our atmosphere, we find that we have very little hydrogen or helium, because hydrogen and helium are the lightest possible molecules. So on average they have higher speeds and they can escape the atmosphere, the gravitational field of the Earth, quite easily. So that leaves us with very little hydrogen or helium in the Earth atmosphere. Let's take a look at an example to conclude this discussion. A tank used for filling helium balloons has a volume of 0.3 meter cube, contains 2 moles of helium gas, 2 moles. The temperature is 20 degrees Celsius, which is 293 Kelvin, and assume the helium behaves like an ideal gas. So part A, what is the total translational kinetic energy of the gas molecules? The average translational kinetic energy per molecule is 1/2 m0 v square bar, and the total translational kinetic energy will be n times the average translational kinetic energy per molecule. So this will be equal to the total translational kinetic energy is n times 1/2 m0 v square bar, which is, using the equipartition theorem, equal to 3/2 kBt, because it's Vx squared plus Vy squared plus Vz squared, 3 degrees of freedom. So I have as a result 3/2 n kBt. Written in terms of the universal gas constant, this would be 3/2 number of moles RT. So whenever you see n times Boltzmann constant, you can replace it by number of moles times universal gas constant. So what is the total translational kinetic energy of the gas molecules? It will be 3/2 times 2, 8.312 joules per mole Kelvin. Temperature is 293 here. So I find that the total translational kinetic energy is 7.3 times 10 to 3 joules. And in part B, what is the average kinetic energy per molecule? Well, I know the total, so if I just divide it by the number of molecules I have, I would find it. So the answer is 1/2 m0 v square bar. It's the total translational kinetic energy divided by the number of molecules n. And what is the number of molecules here? So I have 2 moles, n times Avogadro's number. So it's 2 times 6.02, 10 to 23 molecules. So therefore, I find the average kinetic energy per molecule to be 7.3 times 10 to 3 joules divided by 2 times 6.02 10 to 23. So this will be 6.07 times 10 to minus 21 joules.